Good morning, Calculus 12-0. All right, so today I'm going to start things off by talking about L'Hopital's rule. And L'Hopital's rule is kind of a little bit of an aside. So the next thing we're going to do is some graphing. But I always I struggle a little bit as to when to cover this. I think it's actually a pretty good idea to do it right after logarithms and exponential functions because it can allow us to tackle some limits that involve them in a much nicer way. So L'Hopital's rule is a convenient alternative method of evaluating limits that works in particular cases. So we'll talk about those cases in a moment. But for the meantime, the problem with limits is sometimes when we put the values into the limit to try to assess to see what it's giving us right now, we get something known as an indeterminate form. So indeterminate forms, such as what goes on in the case of sine x over x, the limit as x approaches 0 of that, we have seen already, and we actually proved geometrically that this particular limit gives us a value of 1. But that's not obvious from plugging in the 0 over 0. Now, you might think that it is because since it gives you something over itself that's equal to 1. The thing is, it's not necessarily something over itself. The problem is that it's something that gets really small over something that gets really small. It would be entirely normal for one of those things to get small at double the rate of the other one, or one of them to get small at an exponential rate compared to the other one. If that's going to occur, then you would get a very large imbalance between the numerator and the denominator. So it wouldn't always give you 1. Actually, you can rig it so that you have limits that give you any real number, as well as being able to become something undefined, and we could say like positive or negative infinity. So this happens quite a bit to us when we're evaluating limits, and what we've seen is that sometimes we can pick those apart algebraically. So sometimes we can use factoring or a common denominator, or we can use conjugates, which kind of fits into the factoring idea. But all those methods require us to be able to do something to algebraically change what we're looking at. In this particular case, there is nothing that immediately jumps out at me that would be a good path to take while trying to determine another way to express this algebraically. Sine x is a pretty simple statement in the numerator. We could probably do some weird trig substitutions, but nothing that I think is going to leave me with just an x on the outside of a trig function, which would be what I would need in order to cancel out or simplify the denominator in that case. And again, x just written by itself, it's you could come up with some really complicated expression to mean the same thing maybe, but is it going to be useful? Is it going to actually allow us to simplify things? It's not really apparent. So I'm going to kind of turn the question a little bit on its head, because what we were just saying is that any value could happen, but what really makes the difference if both values are approaching, for instance, 0? So something really, really small. So if one of them at any given point in time was x and the other one was 3x, then they both could be getting very small, but it would always give us a 1/3 ratio. And so what kind of tells us about those values? Well, we just know that they're really small, but the 1/3 ratio comes about from the speed of growth of the top and the speed of growth of the bottom. That 1/3 ratio is actually not only describing what happens if you divide x by 3x, but it's describing how fast the change is of x. Well, how fast is the change of x? Well, it's the derivative. So that would be 1. How fast is the change of 3x? Well, the change of 3x, that changes at a rate with respect to x of 3. And so the 1/3 ratio is describing how fast they're going towards 0 as well. And the speed of approach is actually going to be what tells us what limit they're going to have as a result. So this thinking and the analysis behind it ends up being called L'Hopital's rule. So L'Hopital's rule is a limit exercise, I guess, that recognizes that sometimes when two things are approaching something very, very small or very, very large, you can do positive or negative infinity, as we'll see in some examples that are written in this rule. When you have two things that are approaching, as I said, that value of 0, let's concentrate on first, then it's not the small numbers that we're going to look at, but the rate. So L'Hopital's rule says that if the limit of the numerator is giving us 0, and the limit of the denominator is also giving us 0, or in the case where you get the infinity, so as large as you possibly can imagine, but we'll again just concentrate on zeros for a moment, then the limit of this function divided by this function, which according to our limit rules is the same thing as the overall limit, is equal to the limit as x approaches a of the derivative or the speed of change of the top function, the numerator function, divided by the speed of change, the derivative of the bottom function. Now, this is really easy to get confused with quotient rule because it looks like what you might have wanted quotient rule to be. We wanted quotient rule at the time to be the derivative of the top over the derivative of the bottom. It was instead low d high minus high d low over the bottom squared, or however it is that you like to remember that. So in the case of L'Hopital's rule, it actually is just the derivative of the top divided by the derivative of the bottom in order to get that comparison of the speeds in this particular case, which gives you the overall limit as well. So I'm going to take a look at, actually, before we do that one, let's take the one we know the result of, which is the limit as x approaches 0 of sine x over x. So we've seen earlier in this course that gives us a value of 1, and we did that in a kind of, if you remember the area of the triangle, the area of the sector, and then the area of the larger triangle, and using squeeze theorem. It was quite a process, but this is going to be a lot easier. So first of all, in order to, I'm going to pop back to that other screen, in order for L'Hopital's rule to apply, one of those top two conditions has to be in effect. In this case, if I plug 0 into the numerator, sine of 0 is 0. If I plug 0 into the denominator, that's just a 0 down there. Because of that, I have this type 0 over 0. That's a L'Hopital's rule setup. That is basically this first set of conditions. And so then, according to L'Hopital's rule, if I want to know this limit, I can instead do the limit as x approaches 0 of the derivative of the numerator over the derivative of the denominator. So I take the derivative of sine x. The way that sine x changes is cos x. Take the derivative of x. The way that changes is 1. Now I try to reevaluate the limit by plugging in again, seeing what happens. In this case, as x approaches 0, cosine of 0 is 1. So I get 1 over 1, which gives me a 1 as the final result. That is the answer that we were hoping for. Again, without a whole lot of experience with L'Hopital's rule, you might be a little bit suspicious of that, and that's okay. You might ask me, why didn't we use this up front? Oh, the problem is that we were coming up with derivative rules at the time. We were doing sine and cosine, and it requires you to know how to do derivatives and understand derivatives in order to use L'Hopital's rule. So you kind of like chicken and egg sort of thing. Which one are you going to cover first? And in this case, we did the simple plane derivatives first, and picked through the limits, sometimes the hard way. And now that we have access to this tool, some of that's going to get a lot easier. All right, so evaluate the following limits. So I'm going to do a few of them, see how they go. So this one is the limit as x approaches infinity of ln x over the square root of x. Again, if I try to put this in to my I was going to say calculator, but into my head, I'm going to put a very, very large number into the natural log of x. Now, that is a logarithmic function, but it does grow as you go over to the right. And even though it grows extremely slow, even to get to a million, the number 1 million, you need 1 million place values, basically. If it was a base 10. Not quite the same with a natural log, but it's that sort of exponential relationship there. So that would be kind of wild, but it will get there eventually. Same thing with the square root of x. Actually, it looks really similar to a logarithmic function in a way, but it is growing instead of kind of like logarithmically or exponentially sideways, just by kind of like a parabola laying on its side. But a similar sort of thing. Always grows, always goes up. So if this does give me the type infinity over infinity. Now, that's not helpful. It's not telling me that the answer is infinity over infinity. It's not telling me that the answer is 1. It might be, but we don't know that yet. What we do know is that this is an indeterminate form. So what we're going to do is say infinity over infinity. That's one of the L'Hopital's rule things. So if they're both getting big extremely fast, how fast is one getting big compared to how fast the other one's getting big? If, just as a side note, if one of them was approaching 4 and one of them is approaching 2, it doesn't matter how fast you're approaching 4 or fast you're approaching 2, it's going to be 4 divided by 2 is the ratio. So this only works if they're approaching the same thing, which in the case of L'Hopital's rule, we described it as being 0 over 0 or infinity over infinity. So just be careful that you don't over-apply this when the conditions for L'Hopital's rule are not set up. All right, so the limit as x approaches infinity of, and instead I'm going to do this as the derivative of the top, which is 1 over x, over the derivative of the bottom. So I'm going to think of that as x to the 1/2. The 1/2 comes down front. Now we have x to the negative 1/2. And so I think I know how to evaluate that, but I'm going to switch up the way that it looks anyway. So dividing by 1/2 is the same thing as getting a 2 up top. I'm going to write that x to the 1/2 in the numerator instead of a negative in the denominator. And then that 1 over x is the same thing as a 1 over x out front. The x squeaks into the denominator, so it looks kind of like this. I am actually going to take another step just to make it look very clear. And so x to the 1/2 divided by x is the same thing. It's just the square root of x in the denominator. All right, so this looks different than what we started with. And 2 just stays a 2 when x approaches infinity. But as x approaches infinity, square root of x is going to get really large, the same way it did originally when we had it in the denominator. So we're going to get 2 divided by something that gets incredibly large, which does give us a 0. Now, I actually forgot to set up something here, so just give me a quick second. The magic of Desmos is going to come towards us now. All right, sorry about that. So what we're going to do is I'm going to just do the graph of ln x divided by the square root of x. Now, what we were looking to evaluate this at was actually basically large values. It was as x approached infinity. you can tell that it's not 0 for sure right here. We get values like 0.53, 0.54, 0.529. I'm going to just evaluate this function at a very, well, I'll say large number, 1,000. And it gives us 0.218, and you're like, I mean, doesn't necessarily seem to be closing in on any particular finite value. If I keep putting in some zeros here and evaluate it at a million, 0.0138, it does kind of grows or goes towards 0 quite slowly in terms of the ratio here. It takes a while for the square root of x function to become significantly larger than the natural logarithm of x, but it does look like it eventually gets there, and I could believe quite nicely that that is going to approach a value of 0. But we definitely got that same information doing it using L'Hopital's rule. All right, this one, now there are some other indeterminate forms that you're going to bump into that look a little bit different. So this one's just a multiplication. It's a little bit hokey. So the negative exponent there, it does not take very much effort in order to make this look different. So let's go ahead and do that. The type written at the bottom there is 0 times infinity. So if you have something that's extremely small, approaching a value of 0, and something that's extremely large, and you multiply them together, I guess this is the famous question of what happens when an unstoppable force smashes into an immovable object. So in this particular case, we have the unstoppable force of infinity and the immovable object of 0. Anything times 0 is 0, but infinity is undescribably large. So what happens? It's exciting, we don't know. So the limit as x approaches 1 of ln x over, now remember, the way that we described L'Hopital's rule, it was only defined in the 0 over 0 or plus or minus infinity over plus or minus infinity setting. So this is a very small adjustment here. I took the negative exponent and I just wrote it down in the denominator instead. Now this looks like a typical L'Hopital's rule. So this L'Hopital's rule is going to be evaluating the natural log of x is at 1, gives us 0. In the denominator, 1 minus 1 squared is 0. So this is a 0 over 0 form now. It wasn't looking that way initially, but it was just in disguise. So now that we have it in one of those L'Hopital rule forms, and we're pretty sure that we can use it, the answer to the first limit is the same as the answer to this limit. To the power of 1 times the derivative of the inside, which is just 1. So we basically get that. The limit as x approaches 1. Oh, no. I forgot to switch it over. My apologies. So what I have written down up there, the limit as x approaches 1, just the original thing. And then all I had done was the derivative, so I'll probably not cut this out. I'll let you see all my silly mistakes. So limit as x approaches 1 of 1 over x divided by 2 times x minus 1. So that's the derivative of the top over the derivative of the bottom. If I tidy that up a little bit more, we would have 2x x minus 1. Now, if I put a 1 into that, then I get something very interesting going on here, because this looks like an indeterminate form, kind of. We get 1 divided by 0. Now, dividing by 0 in this case is going to make this extremely large. And so it's not a 0 in the numerator. We get a finite value divided by something very small, very, very large. Now, one of the iffy things here is that depending on what side of positive 1 I'm on, if I was on the right-hand side and I look at this last statement right here, on the right-hand side, I'd get a value that's very small but positive, so it'll be positive infinity. If I was on the left-hand side, which would give me a negative for that x minus 1 bracket and a negative overall, it'd be at negative infinity. So I'm going to say that this answer is that the limit does not exist because my left-handed and right-handed limits there are going to give me different results. Now I'm going to go back over to that graphing thing here, and we're going to do ln x, I guess we already have that, divided by x minus 1 all squared. And so I need to find myself over here. Okay, now at an x value of 1, I'm just going to put that in as kind of like a something to gauge where we are. The idea here is that we have values that are getting increasingly large and negative, values that are getting increasingly large and positive. The limit does not exist at 1, and we were even right when we had that little discussion of which side was going to be positive infinity and which side was going to be negative infinity. If this question had instead had a plus or minus, one or the other in that position, we would be able to answer that the limit is either plus infinity or minus infinity. Which aren't real numbers, but sometimes it's really nice to be able to describe what that limit is actually approaching in those two cases or conditions. So there's another one a little bit different. So this one, the switch over to being like our L'Hopital's rule that we can describe is going to be a fairly small switch. So in this case, I have two separate pieces that are subtracted from each other. You might not know that the, again, depending on whether you're coming in at this thing from the left or the right, the cosecant of x is going to veer off toward positive or negative infinity. So that's probably should fix that actually to being the limit as x approaches 0 from the right, for instance. That's the way that I'm going to write it down here. So the limit as x approaches 0 from the right of 1 over x minus the cosecant of x over 1, basically. All right, so I'm going to change the form of that particular thing by giving it a common denominator. So my common denominator is going to be x. Actually, I'm going to change that cosecant x to a 1 over sine x. So I'm going to say that my denominator is actually x sine x, and then my numerator is going to be sine x minus x. Now, I probably wussed out there a little bit. I could have left it as a cosecant and just had 1 minus x cosecant x. I don't know why I would necessarily choose not to do that, but it's too late now, so here we go. Again, in this form, there's just make sure it's L'Hopital's rule, and sine of 0 is 0, minus 0, still 0, over 0 times 0. So zeros everywhere, and so this is definitely applicable for L'Hopital's rule. So the limit as x approaches 0 from the right can do the derivative, so that's going to be the cosine of x minus 1 over, and then this is actually a product rule. I've got to be a little bit careful. So it's going to be sine x plus x cosine x. And remember that in L'Hopital's rule is the derivative of the numerator over top of the derivative of the denominator. It is not going to be quotient rule. So easy to get kind of mixed up there. Don't do it. The limit as x approaches 0 from the right of cosine. Ooh, cosine, interesting. Because cosine actually isn't going to have a sign change in the numerator. It's going to be 1 minus 1, which is 0. I'm just trying to rethink whether my x approaches 0 from the right is needed. We'll see in a second. So the sine of x is going to be 0 plus, and in this case, ooh, this is interesting. So we're getting a 0 still. Now, the way that this works is we are still able to apply L'Hopital's rule on this if this limit fits the definition, I guess you could say, of L'Hopital's rule, which it does. It gives us a 0 over 0. So I'm going to try applying it again, because that would say that the limit of that last one that I'm looking at, which is actually the limit of the first part of the question, the limit of that yellow highlighted spot, I can apply L'Hopital's rule to and get negative sine x over cosine x plus cosine x plus minus x sine x. All right, now let's evaluate and see what we get there. So we get the limit as x approaches 0 from the right. Actually, I try to evaluate the limit. So we would get 0 over 1 plus 1 minus 0. So we get 0 over 2. In this particular problem, I actually think that the limit exists from both sides. The negative applies to both the cosecant and the 1 over x. So I did a silly thing, and I added that coming in from the right when I was just a little nervous, and I was like, oh man, what if that doesn't work out very well? It will, and it's pretty obvious here that the 0, whether it's no, this is actually going to be, yes, because it doesn't matter. It's going to be approaching 0 from the negative or positive side, but it's not actually, so it's going to be very small positive, very small negative, but it approaches the same value, so we're good. I'm going to graph that again. That's a lot of mumbling to myself this time. My apologies for that. So 1 divided by x minus the cosecant of x. All right, so this thing is pretty nifty looking, and we are specifically wanting to know how this behaves at a value of 0. So at a value of 0, we're right in here. It looks like a really, really well-behaved function, to be honest. It just goes right through the origin, and so the limit as of that thing as x approaches 0 is 0, and it would have been fine whether I had used the plus or minus or neither, which would be the two-sided limit. All right, I'm going to do one more, and then I'm going to let you try some of this stuff out. All right, folks, so the big negative about all this stuff is that you can't be here to tell me how stupid I am when I leave the graph up and you can't see a darn thing I'm doing. So I have reeled it back a little bit, probably about 5 minutes, and we're going to start this particular question over again, which is the limit as x approaches infinity of 1 plus 1 over x all to the power of x. Now, the 1 plus 1 over x, the 1 over x part becomes extremely small, so it's 1 plus a little itty bitty smidgen to the power of really extremely large. That is this case right here, which is 1 to the infinity is what it looks like. We're going to attempt to make this look different. This one is harder than the other ones by a fair bit. It's not obvious how to get it into a L'Hopital's rule, at least from the onset, but this is actually, some of you may recognize it. If you don't, that's okay, but there is a really good reason why you might, if that is the case. All right, now let's go ahead. So I'm going to just actually call this thing y, because I'm going to refer to it a little bit later on. Actually, I don't want y to be the limit. I actually want y to just be the statement, which is this. All right, so now I'm going to say that ln y is equal to x ln 1 plus 1 over x. Now, the reason I can do that, I guess, is because, well, it's just a logarithm rule. So I took the exponent, moved it down to the front. The reason why I would do this is because L'Hopital's rule doesn't say anything about exponents. So it gives me the 0 over 0 or plus or minus infinity over plus or minus infinity. That's not really helpful to have an exponent built into that. So I'm going to change the way that it looks. I'm going to take e to the power of that and then e to the power of that. What that ends up doing is giving us y is equal to e to the power of, and I'm going to write that in a really weird way. So I am going to take that x that's out front and write it instead as a 1 over x in the denominator, because that's going to look like L'Hopital's rule. It's going to be something over something. Now, I'm going to then incorporate my limit back into things, because this right here, y, is the same thing as this, which is the same thing as this, which means I'm actually, if I take the limit of that, I'm trying to answer my original question, which is good. The limit as x approaches infinity of e to the power of this stuff. All right, now, this part, there's no x in the base, so e is just a constant. So when I evaluate what is e to the power of something as x approaches infinity, it's only the exponent that matters what the value overall is going to be. Because of that, I can actually take this limit and have it suck right up into this position up here, because it just affects the exponent. So I get, actually I'm just going to say equals e to the limit as x approaches infinity of ln of 1 plus 1 over x all over 1 over x. So as x approaches infinity, we get the ln of 1 plus 1 over infinity, so it gets really small, which means it approaches 1. The ln of 1 is 0, and in the denominator, 1 over really big number is 0. So this is approaching 0 over 0, which means we can use L'Hopital's rule. So this thing, all on its lonesome, if we were to isolate that yellow bit, it would be a L'Hopital's rule applicable limit, which we're going to go do that right now. All right, so this is equal to e, and then the limit as x approaches infinity, and we're going to change the way that this looks by taking the derivative, and this is going to be a huge chunk of thing. But that's all right. So derivative of a natural log is 1 over whatever was inside times the derivative of the inside. The derivative of the inside is the derivative of 1 plus 1 over x. Derivative of 1 is 0. 1 over x is the same thing as x to the minus 1. So the minus 1 comes down front, now to the power of negative 2. That's the top. And then the bottom is actually the same thing. So that is negative x to the minus 2. And so that cancels out. And we're left with a smaller limit, which is the limit as x approaches infinity of 1 over 1 plus 1 over x. The 1 over x goes to 0. We're left with 1 over 1, which gives us just e. And that is the correct answer, because the original statement, which is, well, what is the limit as x approaches infinity of 1 plus 1 over x to the power of x? That is one of the classical definitions of what e is as a number. So if you actually pop values into your calculator of 1 plus 1 over x to the x power and try really big numbers, so 1 plus 1 over 100 to the 100th power, you start getting into values that are very close to e. All right, I'm going to leave it at that for now. I'm going to have to splice this together so you can see it, but that's all right. I'll upload it in a little bit, and I hope you're doing well. I'll probably talk to some of you soon. We'll have some office hours. Take care.